We've spent a lot of time in this section on geometric series because geometric series are lovely. They add to specific values that we know based on a formula, and that's actually quite unusual and rare in the infinite series world, as we will soon discover in later sections. Before we leave this section behind, though, we want to talk about a couple more small topics. The first is that infinite series have properties. If we know that an infinite series adds to a number, and another infinite series adds to a number, and then we have some constant c that is a real number, then the following three things are true. If I take my infinite series and I multiply every term by that constant, then I'm just multiplying the sum by that constant. Lovely. And that would work for geometric series, hint, 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 because geometric series are the biggest and most common series that we use that we know make specific numbers like this. 99%, well, I shouldn't say that, 90% of the series we work with will not be geometric, and therefore we won't know specifically what they add to most of the time. All right, so then what if I had two series that I added up and they each added to a specific number? Well, then their sum would just add. And similarly, if they subtracted them, then their sum would just subtract. Simple as that. Geometric series aren't the only ones that these properties are true. These are actually properties that are true just in general of infinite series. However, geometric series are some of the most common ones we use since we specifically know what those values a and b would be based on our formula from from theorem 10.7. All right, so let's suppose that I have this infinite series and it makes 5, and this infinite series and it makes 8. Then find the following. The sum from a to infinity of 30 times a sub n would be 30 times what the sum would be, which was 5, which is 150. Now you'll notice in these properties, it doesn't have to start at 0. Geometric series start at 0 for their basic formula. So the basic formula starts at 0 because that's how we make it work, right? So we make them start at 0 here. But of course, we've learned that we don't have to start at 0. We just have to make modifications when we don't start at 0. We have to make adjustments by subtracting off the partial sum, right? So these still converge. They converge to specific values, right? So these properties do not have to start at 0. They just have to start at the same consistent value. So I have to start at a for both a sub n and b sub n, which they do. So I'm fine, right? So if this was 7, then this one's 7. They have to start at the same spot. This one would be 5 plus 8, which would be 13. And this would be 5 take away 8, which would be negative 3. There we go. Simple as that, right? So those properties are rather simple, but they're important. And they're how we can make combinations of series that we know. So we can take series that we have known sums for, and we can add them, subtract them, and combine them, multiply them by a constant, and so on. Now there is one other series that we can figure out the sum for in a slightly tricky way. So it's using something called the method of differences. So rather than having a formula for it like we did for a geometric series, a telescoping series is a series whose partial sums eventually only have a fixed number of terms after cancellation. And that cancellation technique is known as the method of differences. Now it sounds super convoluted, but it's actually pretty simple. Let me show you. So I'm going to start with this series right here. So I have the cosine of 1 over k minus the cosine of 1 over k plus 1. There's the sequence. And then I'm going to add it from 1 to infinity, which turns it into an infinite series. So I'm going to find a formula for the nth term of the sequence of partial sums, s sub n, and then I'm going to evaluate the limit as n goes to infinity of s sub n exactly. Okay, so let me show you how this works. So let's start with k equals 1. Right? So when I put k equals 1 in there, what will happen? I'll have the cosine of 1 over 1 minus the cosine of 1 over 2, because 1 plus 1 is 2. All right, so there's the first term right there. K equals 1. Plus, it's a series, so I have to add. So now let me do k equals 2. Okay, so I'm going to put 2 in there. So that would be the cosine of 1 over 2 minus the cosine of 1 over 3. right? 1 over 2. 2 plus 1 is 3, so 1 over 3. Plus, and hopefully you realize where this is going, but maybe not yet. Maybe it's a little too soon. So if I put in 3, I would get the cosine of 1 over 3 minus the cosine of 1 over 4. And would just keep going like that. All right, so far, what's the problem? Well, do you see the problem? Because I do. Look at this. I'm minusing the cosine of a half right here, but then I add it right here. They cancel, right? They're different from each other, right? Differences, method of differences. So minus plus disappears. What about this one? Minus the cosine of a third plus the cosine of a third. This will be minus the cosine of 1/4 plus the cosine of 1/4 will be the next one, and so on and so on and so on. So what's going to happen is that it's going to keep canceling. So if I have, and let's see what it says after cancellation. So if I did k equals n minus 1 right here, it would be cosine of 1 over n minus 1 plus the cosine, minus the cosine of 1 over n. And then let me do k equals n right here. So you can see what's going to happen. You'll have plus the cosine of 1 over n minus the cosine of 1 over n plus 1. And it would just keep going like that. So whatever term I pick, I'm going to have cancellation going on. These are going to go, right? This one and this one. And then this would cancel with the next term, and this one cancels with the one ahead, and so on and so on and so on. So basically everything cancels out except for what? So this one's going to go with the term that's right here. This one will cancel with the term that's right here. This one will cancel with the term that's right here, right? And that would keep happening over and over and over wherever you are, except for one bit. This bit right here. This is the only part that does not cancel. Okay, so that means that I know that the sum of this series must be equal to the cosine of 1, period. Right, that's what a telescoping series looks like. And this is the limit as n goes to infinity of our partial sums, right? So if you take your partial sums and you keep adding to infinity, you're going to get this value because everything else cancels. Oh, it occurs to me I forgot to answer that other question. So it says find a formula for the nth term of the sequence of partial sums. Sorry, I didn't do that. So this right here is the answer to what's the limit. So the limit of the series is the limit of the partial sums as n goes to infinity, right? Partial sums are bits of the infinite series, and if you let n go to infinity, then it is the infinite series. So this is the same thing as saying what's the sum of the infinite series, right there. But then I forgot to answer the find a formula for the nth term. Okay, so it was in here. It was part of what I was doing. So it's going to be the cosine of 1. This goes away, that goes away, that goes away. Where we want to look is right here at the nth term, because they want the nth term of the partial series right here. So that would be nth term of partial series, of the sequence of partial sums, I should say. Let me just write it that way. Would be cosine of 1, right here, because that never goes away. Cosine of 1, this part is gone, that part is gone, that part is gone. Everything is gone except for right over here. So that part right there. Let me uncross that off just for you guys to see, right? So if this is the nth part, this part does cancel because that piece was already written. We already wrote minus cosine of 1 over n plus cosine of 1 over n. So when you're getting to your next term, what's the part that hasn't been canceled away yet? It's the cosine of 1 over n plus 1. That part hasn't yet gone away because I haven't yet written the next part, right? So plus dot, dot, dot. So if I'm talking about the nth term, which is this one right here, that nth term would have minus the cosine of 1 over n plus 1. That's the nth term of my series. Because everything else between this bit right here and this bit right here has canceled away. They've all added and subtracted with their compatriots, right? They had their opposites in there. The only part that hasn't yet canceled away is this part right here. It will cancel away in the n plus 1th term, but they weren't asking me about the n plus 1th term. They were asking me about the nth term.